All right, welcome back, guys. I've got another example here for you that's going to help you out with question 2 on page 5, page 6, 7, 8, and 9. Okay, question 2 is going to be with a parallel circuit. Notice I just changed that up. Evaluating a parallel circuit. I've already colored in my wires. I'd suggest you color those in. That gives you a clue right away. That clue is that this 24 volt difference, we're going to visualize with the red blue. Notice the red blue shows up. That's going to give us a clue for in a couple of steps down the line here. Now, the first thing I want to do here is recognize I've got a table set up to evaluate the whole circuit. I've got a 48 ohm and a 24 ohm resistor connected in parallel to each other. I want to figure out that total resistance. Okay. Before I even do that, let me just point out the battery itself is a 24 volt battery. That's going to be the total voltage of the whole circuit. Okay, so we've got that going for us. Let's figure out what that total resistance is here. I've got a sideboard over here that we can take a look at. All right, to find the total resistance, remember that equation is going to be 1 over total resistance equals 1 over resistor 1 plus 1 over resistor 2. So let me do that in a couple of steps here. 1 over my total resistance equals 1 over 48 ohms plus 1 over 24 ohms. And now you can do this a couple of ways. You can use your calculator to figure out what that total resistance is, or we can recognize that there's a fraction here that's pretty common. 1 over 48 plus 2 over 48 is going to equal 3 over 48. And now keep in mind, we don't want 1 over my total resistance. We want total resistance over 1. And that's going to equal 48 over 3. Okay, so we took the reciprocal of the left side. We're taking the reciprocal of our sum over here. 48 over 3, help me out with that math. You can check on your calculator. Looks like it's going to be 16 ohms. There is our total resistance here. Okay, so I'm going to box that in right here. Okay, I want to do one of those examples for you visually also. I know we showed a couple of examples on still life, right, that I've got posted online, but I want to just see that one time here. Okay, so we've got the total resistance now for our circuit. I want to fill that in right here. 16 ohms is my total resistance. 24 volts is my total voltage. Okay, we're going to go back to Ohm's law here. Voltage equals current times resistance. Just like we did before. Now you can see that voltage and resistance are both given. We can solve for our total current, and that's going to go right in here. Okay, so the way I'm looking at this is 24 volts equals current times 16 ohms. If I divide both sides by 16 ohms, okay, I'm going to get my total current, and double check my math here for me, but it looks to me like 24 over 16, I think that's 1.5 amps. Okay, so let me put that over here. 1.5 amps is my total current. All right, just for visual purposes, you might look at that as current coming out of the battery like so. 1.5 amps left the battery. Okay. Okay, so I'll fill that in right over here as well. There's my 1.5 amp current. That's the total current coming out of the battery. Okay. Next step here, we can look at power one more time here. I'm gonna have to put it on this side. Power equals current times voltage. Current times voltage, 1.5 amps times 24 volts. Okay. Help me out with the math there. 24 times 1.5. Is that 36? Yeah, I have to double check my math on that, but I'm pretty sure power equals 36 watts. I'm going to put that right in here. All right, but we'll come back to that in a little bit. We'll see if we've got that correct here shortly. Okay, now, the next step here, I want to recognize what is it that we know next. We found all of our totals. That's a great start, but now that we've got that, we have to figure out where can we go from here. All right, can I just fill in 1.5 amps for each of these? That's where we got to be careful. If you go back to this page and you look at a parallel circuit, okay, here it says all the voltages should be equal for the individual resistors. Here it says all the currents should add up to the total current. So I'm thinking in here, they're not each necessarily going to have 1.5 amps. I think these currents are going to add up to 1.5 amps. The current that gets to this point right here, 1.5 amps, is going to split up, where part of it goes this way and part of it goes this way. All right, we'll get to that in a little bit. But the thing that we do know is that the voltage of 24 volts across our battery, that red-blue color difference, we've got the same red-blue color difference here, same red-blue color difference here. I want to point out, for a parallel circuit, if I was walking around the room looking over your shoulder at how you're doing here, I'd want to look at this column right here, and I would know you're doing it correctly. If I saw that in a parallel circuit, you put 24 volts is across my 48 ohm resistor, 24 volts is across my 24 ohm resistor. Now we're in business. Now we've started to evaluate the whole circuit. Remember, Ohm's law allows you to figure out voltage, current, resistance for the total circuit, but we can also use that same Ohm's law for every individual resistor here. If you know 2 of these 3 variables, you can solve for the other. Here we know 2 of these 3 variables here. Voltage equals current times resistance. Okay, looks like 24 equals current times 24, and we can do that math right now. Pretty sure that's going to be 1 amp going through there. Okay, here, maybe I will do this one time. I'll put this in here for the other resistor so that you can see. 24 volts equals current times, well, let's put in the 48 ohm resistor. Okay, let's divide both sides by 48. 24 divided by 48, that's going to give us 0.5 amp. Okay, and now let's just stop for a second, because we're right there. We're just about done with this. But if you recall, what do we know about current in a parallel circuit? The current coming out of the battery is going to split up into current through those individual resistors. The sum of those currents should add up to the current going through or coming out of the battery. Okay, and that seems to work out. That's consistent with what we tested in our lab work. Okay, so we're one step away. Let's figure out power, and we'll be all done with this example. Power is always going to be current times voltage. Current times voltage, we're all set. 1 amp times 24 volts, 24 watts. 0.5 amp times 24 volts sounds like 12 watts. And here's another concept we haven't talked about from the lab, or from any labs, but I want you to recognize this is something that is going to be consistent here. Whether we're talking about series or parallel circuits, turns out that the total power should equal the power of the individual resistors added up. 12 plus 24 comes out to 36 watts. We're going to notice that with all these examples that we do, the powers will add up to equal your total power. Here's what I think of. If you have a 12 watt light bulb and a 24 watt light bulb, and you turn those both on, you know what you get? You get the sum of those light bulbs, okay? You get the sum of their brightnesses adding together to give you a total wattage in the room. So there's the example that we're going for evaluating parallel circuit. Again, I just want to point out which one we're dealing with here. We're looking at question 2 on all of these pages, page 5 through 9, question 2. That same concept is going to show up over and over again. You've got a common voltage for all those. I'd say let's do all those, do as many of those as you can, and we'll come back later and we'll talk about this type of circuit later. Okay, that's definitely going to be a little bit trickier. All right, so as long as you got these basics, I think we're going to be in really good shape. Hey, we'll talk to you a little bit. Try these out when you over these next couple days, and we'll be back together here shortly.